The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we're scaling back. Way, way back, and looking at the big picture, our universe. A little later on, I'll sit down with astrophysicist Roberto Trotta to talk about his new book, The Edge of the Sky, All You Need to Know About the All There Is, where he tackles some of the most complex concepts in cosmology in an unusual way. But first, I'm happy to welcome back theoretical astrophysicist Ethan Siegel. I'm here with Ethan Siegel, theoretical astrophysicist and professor at Lewis and Clark College in Portland, Oregon. He has previously taught at the University of Wisconsin, the University of Portland, and done astrophysics research at the University of Arizona. He writes the blog Starts With a Bang on the Medium Network, and occasionally pops onto our show to lend us his cosmological and astrophysical expertise. Ethan, it's always good to have you back.
Thank you, Rochelle. It's my pleasure to be here.
Okay, so back in April when it was first announced, we actually had Phil played on to give us the Cliff Notes version of what Bicep 2 was all about. But since new information has surfaced, we wanted to sit down and dig in a little deeper here. So probably the best place to start is the beginning. Can you walk us through what the Bicep 2 project is and what it was looking for and why they were looking for it?
All right, so there are two beginnings here. When we say beginning, we can talk about the beginning of Bicep 2 and what that experiment is, but we should also talk about the beginning in the sense of the Big Bang and what it's looking for when it does its thing. So what Bicep 2 is, this is a South Pole experiment. It's looking up at a very small region of the sky, maybe only 5 to 10 degrees on the sky, about the size if you took your hand and you closed your fingers and you held it up at arm's length. You're looking at about your 3 middle fingers together. You're looking at about that size of an area on the sky. What Bicep 2 is looking at is it's looking at not only the leftover glow from the Big Bang, right? That's the cosmic microwave background, this 2.725 Kelvin radiation. It's looking at a specific signature called polarization in that light. And what it's looking for is it's looking for specific patterns and specific signatures that would be indicative of certain processes that happened very early on in the universe. So that's the short of the experiment. Now, let's go back to the Big Bang as well so we can talk about what it's looking for. So when we go all the way back to the very, very, very beginning, right, it turns out the Big Bang isn't the very first thing that happened in the universe. When we talk about the Big Bang, we think about how our universe today is expanding and huge and has these huge overdensities like stars and galaxies and clusters of galaxies, and these huge underdensities like these great cosmic voids, or the fact that the distances between giant clusters of galaxies are tens of millions or even hundreds of millions of light years. And we think about how things got to be this way. The universe is expanding because things were closer together in the past. The universe is cooling from a state that was hotter in the past. And things are so sparse today because the universe was denser in the past. So we could go all the way back to a very hot, very dense, very rapidly expanding state. And that's what we call the Big Bang. But that wasn't the very beginning. As far as we know, there was a state before that where the universe was just empty space with a huge amount of energy intrinsic to it. That was a period called cosmic inflation. Now, it didn't stay that way forever. It had to come to an end. And the way cosmic inflation came to an end, we're pretty sure of this from observations we've made of the initial density fluctuations in the universe, are we say, okay, we had this energy intrinsic to space itself. It made the universe expand at an exponential rate. And at some point, the energy that was in space itself got converted into matter, antimatter, and radiation. And when that happened, that's what we consider to be the Big Bang. And then things expanded and cooled. We were able to form atomic nuclei. We were able to form neutral atoms. Gravitation was able to start collapsing the overdense regions into stars, galaxies, and clusters. And fast forward 13.8 billion years, and we've got our universe today. So what BICEP 2 is looking at, now, coming back to all of this, what BICEP 2 is looking at is it's going back and saying, I'm looking at the radiation from when we first formed neutral atoms, from only 380,000 years after the Big Bang, and I'm looking for very specific signals that were imprinted on this from even before, from all the way back at the time of inflation. So that's the goal of BICEP 2.
So it seems like the goal is really to find more evidence for cosmic inflation. Is that correct?
That would be what I would say is the best opportunity for success that it has. Like, if you were a scientist working on this and you were optimistic and say, we're going to measure this thing in a dream world, what would we find? The answer is you would find a signature that came from the inflationary era of the universe that showed up in your signal. That was something that you were the first experiment to be sensitive enough to detect.
Okay, so back in April, there was kind of a big announcement. Can you walk us through what they found and announced?
Okay, so let's talk about now what BICEP 2 actually measured. The light that comes from this leftover glow of the Big Bang, it's traveled to us 13.8 billion years since it was emitted. Because the universe is expanding, it's even farther away than that now. It's some 46 billion light years away right now. But what happened is BICEP 2 said, we're looking at this light and we're seeing how it's polarized. Okay, so light, remember, is made up of it's an electromagnetic wave, which means it has electric fields and magnetic fields that oscillate in phase with one another. So polarization talks about if you have this electromagnetic wave and it interacts with an electric field, it's going to respond in a certain way. If it interacts with a magnetic field, it's going to respond in a different way. So we have what we call E modes for polarization, which is the interaction of the electric part, and B modes, which is the interaction with the magnetic part. Now, inflation leaves you a few extra things. One of the things it leaves you density fluctuations on all scales in the universe. You know that the universe is a quantum universe, right? We have quantum field theory is the law of the land. So that means empty space itself has these quantum fluctuations inherent in it, where you have a fluctuation towards overdensity. That's going to result, as inflation stretches that across the universe, in places where you're more likely to form stars and galaxies and clusters. Where you get an underdense fluctuation, those are places that are going to give up their matter to the overdense regions. Those types of fluctuations, those density fluctuations, we've already observed. We've seen those with satellites like COBE and WMAP and Planck. And this is good, BICEP 2 sees them also. But what BICEP 2 also sees is how those density fluctuations interact with polarization. So they see signatures in both the E modes and the B modes from that. Now, there's a second type of fluctuation that happens during inflation, and that's a fluctuation in the gravitational field itself. Not because there's extra density or less density, but because there are ripples in space-time itself. These are known as gravitational waves or gravitational radiation, depending on who you're talking to. These are going to interact with the leftover light from the Big Bang also, but they are not going to make E modes at all. Gravitational waves only interact with the B modes. They only make a B mode polarization signature. So what BICEP 2 said is, we were able to look at this light. We saw the density fluctuations that we knew we should see. We saw the E and B modes that looked like they were from the density fluctuations. And then they said, we found these extra B modes that we believe are evidence of not just inflation, but of one specific type of inflation, because inflation has a few different models that will work, including two very simple ones. And what BICEP 2 said is, we see inflation that's consistent with this one particular model and not the other one. And that's why it was such a big deal, because they said, here's what we detected, and the statistical significance at which we detected it is past the threshold for claiming discovery. That's why it was such a huge announcement.
So fast forward to September. We heard more about the BICEP 2 results, and it was not so exciting. What happened? What do we know now that we didn't know in April?
Well, here's the thing. We say, yeah, E modes and B modes from the Big Bang, from the density fluctuations, from gravitational waves during inflation, from the earliest stages of the universe. That's true. All of those things will polarize light. But here's the thing. There are other things that are going to polarize light. Remember, we said it was emitted. This light was emitted 380,000 years after the Big Bang, but it has had to travel through 46 billion light years of space to reach our eyes. It has had to travel for 13.8 billion years in time to get to us. And during that time, it has passed through all of the matter and the intergalactic mediums and gas clouds and our own galaxy before it's able to reach us. So when we look at this small region of sky and we see this polarization signature, yeah, we can chalk some of it up to density fluctuations. We can chalk some of it up to the E and B mode polarizations induced by the matter field. But these leftover B modes, these extra B modes, are we sure that they're really due to the primordial gravitational waves from inflation, or could it be that it's due to what we call foreground, or stuff that exists in between when the light was emitted and our eyes? What BICEP 2 initially did, and this is a very clever thing that they did, but it's not necessarily as robust as we would like, is they said, we took a look at the Planck maps, because Planck does all sky coverage and they release their data and make it public. And they said, we're going to go and take these maps and we're going to extrapolate what the polarization signature from the dust is in this region, and then we're going to take that out. What happened in September is Planck came out and said, hey, we know we haven't released our polarization data yet, but we took a look at what you did, BICEP 2, and we don't think you did it correctly. It's not your fault because you didn't have our data. You did the best you could with the limited data we had, but we've got the polarization data now, and what you said the foregrounds should be are not what the foregrounds actually are. So now there's this tension, right? If the foregrounds aren't what BICEP 2 said they are, then we don't have a discovery of gravitational waves. We may have detected something that could be as simple as dust and gas in our own galaxy and confuse that for a signature from way back in the prehistory of the universe.
So what I find really interesting about this case is that it's both a perfect example of science in action and also kind of an example of science gone a bit wrong. I mean, the process of science is self-correcting, and that's what we see here, which is exactly how it's supposed to work. But it's also showing us how initial results can get blown up by the media too soon, and while we usually point fingers at the media itself, it also seems in this particular case, we've got maybe an example of some of the scientists themselves sort of encouraging this premature response.
You know, there's a famous quote from Feynman that I really like, and he says, "The first rule of science is you must not fool yourself, and you are the easiest person to fool." And what he meant by that is when you are passionately working on something and looking for something and excited about something, when you have an idea, when you have an experiment that you're invested in, you want the groundbreaking results. You want the earth-shattering results. And so you can fool yourself by doing something that it's so easy to do when you work on something scientifically, is you say, here's what I'm going to do. I'm going to take into account everything that I can think of. I'm going to take into account all the effects that I can imagine to the best of my ability. And I'm going to estimate the uncertainties and the errors on them to the best of my ability. And then I'm going to do my analysis and I'm going to see what's left. And when I see what's left, what does that result look like? And if that result looks like it's meaningful, if that result looks like it's groundbreaking, you stop and you say, wow, eureka, we've got it. But that's not always the right way to go. There are two types of errors that we make as scientists, and these are errors that are inherent to the scientific process. It's not like, oh, you made a mistake, we're going to have some other scientists go and do it better. One of these errors is statistical. This is one of the types of errors. It says, you know, when you go out and you measure something, you can only know what things are like on average. You can only know what things you see to a certain confidence level because you don't have an infinite number of things to measure. So I told you Bicep 2 could only measure 5 to 10 degrees on the sky. So they are limited by the amount of data that they can take. They are limited by the amount of sky that they can observe. So that's a statistical limitation. But there's also a systematic source of error, which is, oh, I took density fluctuations into account, and they have that error associated with them. And I took gravitational lensing into account, and it has that error associated with it. And I took the temperature of the experiment, the fact that it's not at absolute zero, into account, and that's the error associated with it. And these are systematic errors. The problem is you can never perfectly identify all of the systematic errors. And they thought we've really done a great job identifying the systematic errors of galactic foreground. And it turns out they may have vastly overestimated how good they are at that. In other words, this one particular source of systematic errors may be much larger than they had initially stated. And that is their fault. That's their fault for saying, well, for not saying we may have underestimated our error, because they did. It looks like they did underestimate their error. But at the same time, that's a difficulty inherent with systematic errors always, is you look for them. You look for all the ones you can think of and you estimate them to the best of your ability. And sometimes, especially in their case where they didn't have all the information, they didn't know what it was that they didn't know, it's forgivable. It's kind of a similar situation to me from, do you remember a couple of years ago when the Opera experiment claimed to detect faster than light neutrinos?
I was just going to mention that one.
Well, you should. It's very apropos of this, because what happened over there is they had all of their errors. They had their statistical errors. They had their systematic errors. They took into account everything that they thought of, and they were seeing this consistent faster than light signal. It was statistically significant. They had taken into account everything they knew of, and they actually came forward and said, we kind of think this shouldn't be right, but we don't know where we've erred. We don't know where we've made a mistake, but either we've made one or we've just discovered something groundbreaking. It turned out to be a loose cable. That's a systematic error that you can't plan for, that you can't know about. This one, I would say, is a little more difficult because I think if they had done a little more due diligence, they would have known, yeah, we don't really know this to the level of certainty that we want. But it could still be there. This is something that Planck is set to release their full suite of polarization results this coming month, this coming November. So certainly by time the year is out, we should have an accurate measurement of what is the signal due to gravitational waves from the early universe versus what is the signal from foreground, from galactic gas and dust. And we should be able to see, is this evidence of that one particular model of inflation that predicts these large gravitational waves, or is this actually evidence against it? And that's something we should know by the end of the year.
So I want to just quickly jump back to that original press release and to some extent to some of the other big science news. I'm thinking specifically big physics science news that we sometimes hear, where they often will jump right into a press release before some of their research has been fully peer-reviewed or refereed. Why have those big announcements, those kind of big media events, before you go through what we kind of understand to be the process of science?
You know, this is something that I would say is good and bad about the way media has sort of changed. You know, I've done science writing, professionally now for a number of years, and I've watched the whole landscape of things change. One thing that's gotten very hard in recent years, and I would say it's pretty impossible right now, is to keep secrets. You can't keep a secret under wraps. You can't say, oh, we may have just found something that changed the world. Let's be careful about it before we tell the world about it. That's not ever going to happen anymore. Not with Twitter, not with people breaking embargoes all the time, not with unethical me-first journalists. It doesn't need to be the majority. It just needs to be one. And I would say the way media has changed, we're not going to have that anymore, not unless it's something that people don't realize they care about. We live in a world now where people need to know and are going to find out, hey, here's this cutting edge thing that may or may not be right. I can't say, oh, let's just have everyone in the whole world be scrupulous and careful. That's never going to happen. That's not the world we live in. I'd love it to be, but I think it's naive to expect that that's even a possibility in this world. So I think we have to be prepared to say, hey, people are going to do what they're going to do. The best thing we can do is try to remind everyone, when we do this, you have to be careful. When we do this, we have to check it. We have to vet it. We have to remind people, here is what the process of science is. And this that you're hearing about now, this was a first step towards getting there. This is what this team found. Will it hold up? Maybe, maybe not. Will it pass peer review without major changes? Maybe, maybe not. But we can tell you about it. That's okay. But let's be completely honest with what we're telling you. There are plenty of news outlets, and I'm not going to name names. You can figure it out for yourself. There are plenty of news outlets that are never going to do that. There are plenty of news outlets that are going to put out the piece of clickbait, that are going to put out the most sensational headline, that are going to put out the thing that's going to make you want to read about this piece on their site more than anything else. And there's very little you can do about that. If you say, well, here's this new paper that was submitted to the preprint archives, people are reading that. And if someone doesn't come out and give well, here's the full press release, then people are going to read that and they're going to make their own generally ill-informed interpretations of what that is. I'm not sure that that's even better. So yeah, there was a media fiasco. It is arguable that overall this resulted in a negative perception of science and how it worked. But on the other hand, I think we have to be pretty sensitive to this is the world we live in, and there really isn't an easy answer for how should we have done this properly. I would say the only thing is it would have been better had we put more caveats in there when we generally spoke about it. But that's the responsibility of both scientists and science journalists. And it's something that people haven't really expressed an appetite for. So even though I personally am livid about it and tend to be extremely critical of it, I'm also kind of forgiving of recognizing I'm swimming against the tide here. This is not something that the world is going to go and be the way I want it to be. This is something where we're going to have to figure out a way to get the information out there accurately nuanced in the world we have now.
The internet is one of those things that is just amazing, but complicates everything.
Yeah, and I'm sorry I couldn't give you a more I've thought about that, and here's the answer, and here's how we're going to solve that problem. I don't think I have an easy answer to that. I'm not sure there is one.
I would definitely agree. I personally have the takeaway of I'm just really glad that people are still excited enough that these things get a lot of coverage. I'm just excited that things like neutrinos and cosmic inflation and the Higgs boson, that people get excited about it. So as long as that still happens, I think the rest of it we can deal with.
Well, let me tell you, Rochelle, the thing that I'm excited about this is whenever a story like this breaks or gets really big, for someone like me who says, hey, I actually am an expert in cosmology and astrophysics, it represents a tremendous opportunity to get out there and say, hey, you're excited about this news. You're excited about how this might change the world. By the way, would you like to actually know what the world is confident about scientifically at this point? Would you like to know what the cutting edge science actually tells us about the universe in 2014? Would you like to know how we got there and what we've learned and why this is the cutting edge and what it means, whether it turns out to be true or whether it turns out to be a phantom? I think that opportunity for education is a good thing that does come out of even, I would say, premature science like this.
I'm curious, from your experience as a teacher and also from your experience as somebody writing for a lay audience, do you find there's more engagement now than there used to be?
I think it goes in waves, and I think that I get a biased viewpoint of it because the people who I tend to engage with are people who tend to already be interested in science. I try to reach out and my philosophy on it is science is for everyone, whether you're religious, whether you're an atheist, whether you're somewhere in between, whether you have an advanced degree, whether you are still a teenager, whether you are an adult with a teenager's education, it doesn't matter. Science and the process of science and the body of knowledge that science is something that I think everyone should be able to share in the wonders of. I don't know that people are more or less interested in it now, but I think people are more aware that science is something that can be accessible to them if they make the effort to go out and find it, if they make the effort to go and find the right speaker to listen to, if they find the right voice to listen to. I'm not always necessarily pleased with the voices that they choose, but I do think that people do have a better awareness of the accessibility of science than they used to. I'm not sure that people have a better appreciation for what science actually is and does than they used to. But I think that we have made improvements in general over the past few decades where people do think science isn't necessarily something that's closed off to them unless they themselves are scientists, that they sort of recognize, you know what, if I went out and looked for it, or if I paid attention to what was going on, or if I found the right sources, I would find that science is for me exactly as much as I care for it to be.
Ethan, thank you so much. You're great.
Well, thank you, Rochelle. Thank you for an incredibly stimulating discussion, and thank you for giving me the freedom to go and meander down some pretty advanced cosmological rabbit holes here.
We love your meandering, so please come and meander again.
Awesome. I'd be more than happy to.
If you want to learn more about Ethan Siegel, his work, or theoretical astrophysics, I definitely recommend checking out his blog Starts With a Bang, which you can find on the Medium Network. And we'll be sure to include a link to him on our show notes at our website, scienceforthepeople.ca. Up next, I'll be back with another astrophysicist, Dr. Roberto Trotta, to talk about his new book, The Edge of the Sky, All You Need to Know About the All There Is. Stay tuned.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
The All There Is started from a single point, but then grew very, very quickly to become very, very large. It is almost not possible to picture how fast it grew. Imagine breathing into a colored party ball so that with every breath, the ball becomes 10 times bigger than before. If every breath took you an hour, you would have to keep going for over 3 days to make the ball grow as much as the All There Is grew right after the big flash. By that time, your party ball would have become much bigger than the white road, so that 100 party balls would fill the entire part of the All There Is we can see. We don't know what made it grow so much, so fast. You're listening to Science for the People. That was a brief excerpt from Roberto Trotta's charming new book, The Edge of the Sky, All You Need to Know About the All There Is. Roberto is here with me now to talk more about how this book came to be. With me is Roberto Trotta, an astrophysicist at Imperial College London, where he studies dark matter, dark energy, and the early universe. After earning a PhD at the University of Geneva, he was a Lockyer Fellow of the Royal Astronomical Society at Oxford University before being appointed as a lecturer at Imperial College. He's published more than 50 scientific papers, contributed to 2 books, and received numerous awards for his research and communication of science. He lives in London with his wife and daughter, and he's here to talk about his new book, The Edge of the Sky, All You Need to Know About the All There Is. Welcome to the show, Roberto.
Thank you, Rochelle. Great to be here.
So, where did you get the idea for this book?
Well, the idea came from a website I stumbled upon last year called the 1000 Words of Science. It was a website which challenged the readers to try and write up their job description using the most common 1,000 words in English. But actually, the idea originally came from an XKCD cartoon. So the creators of the website had gotten their idea from the so-called UpGoer 5, which is a cartoon created by Randall Munroe, who is the guy behind the XKCD website, which recounts a number of stories and jokes using geeky and stick-like figures. And so what Randall had done with the UpGoer 5 was to take a sketchy picture that he had drawn of the Saturn V 5 moon rocket and label it using only the most common 1,000 words. And so, because it didn't have the words Saturn and moon and rocket to name the Saturn V rocket, he called it the Upgoer 5 because it goes up. And those words were available in the 1,000 words list. So that's where the idea originally came from. And when I stumbled on this idea, I thought that it was a brilliant idea to play with language. And after I tried it out by writing up in a few paragraphs my job description as an astrophysicist, which was an incredibly frustrating exercise at the beginning. It was so difficult to do. Later I thought, well, actually, here is a great format. Perhaps I can stretch it a little bit more and make a book out of it, and a book in which I can recount the entire history of the universe without even using the word universe.
So, the 1,000 most common words, a list of which you actually include in the book, which I read in its entirety because that was really interesting as well. Where did you get this list from? How was it generated?
The list itself is something that really interested me as well. As you say, the first time you go through this list, you're very astonished to find certain words in there that you wouldn't expect necessarily, and many other words that you think you'd be there are not on the list. So initially the list, I just mutated the very same list that the 1,000 Words of Science website was using, which itself came out of a Wikipedia entry, which claims to have culled the list from 9 million words of contemporary fiction online. Whatever that means. And of course later on when this project started becoming more important to me and the first draft of the book was ready, I started questioning the accuracy or indeed the origin of the list. Clearly, if you were to take another set of words and works to select the list from, you no doubt end up with a different set of 1,000 words. And so eventually I came around the idea that what the list exactly is and where the list precisely comes from are immaterial questions to what I'm trying to do. In a sense, all sets of rules are arbitrary to an extent, and so are mine. And my rules are that I'm going to use these 1,000 words, which might or might not be the truly most common words in English, but for sure, those are very simple words. And it's a list of 1,000 words that does not include some interesting words that I would have liked to have for cosmology and certainly to talk about the universe. But the fact that those words were not on the list was what really forced me to come up with different ways of talking about the universe. And that is what interests me in the end. Whether the list is really the list of the most common 1,000 words, I don't know. Probably not. But once I had this list and started working with it, my question was, what can I do with it, and what kind of picture of the universe emerges from such a restricted, pared down, very Spartan lexicon?
It's really interesting that you say the list was generated off a collection of books, because I can imagine that if there had been a different genre of books, for example, maybe something like science fiction, your work might have been a little bit easier.
Absolutely, but perhaps less interesting in a sense, because I later came to realize that precisely the fact that I was missing some what I thought were crucial words in the list. I couldn't use energy or planet or galaxy, universe, and so on. All these words I didn't have in the list, and if I had them, perhaps my book would have been a little bit more traditional, a little bit less experimental, but to me less interesting in a sense. And so it's really the fact that all those words are not in the book that makes the experimental side of it a little bit more challenging, I think, and hopefully the result a little bit more different than any other science book you might have read before.
So how did you actually go through the process of writing this book, making sure you only used words from that list? Because that seems within itself to have been perhaps a frustrating experience.
Yes, at the beginning I started by doing it by hand, but then I quickly realized I wasn't going anywhere. It was taking me too much time, and cross-checking the words was too complicated. And so I ended up writing a little piece of computer code that had the list of words inside it, and it would check all my writing to check for mistakes and words that were not on it. And so with the help of that computer program, I was able to write more fluently, and also little by little I started getting the hang of it. I actually learned out which words I could use and which I couldn't. And whenever I thought of a word that I knew wasn't on the list, little red flags went up in my mind telling me, no, you can't use that, so you have to find a way around it. And so, but the second half, or the last third of the book or so, was much better. It was like I had learned this new language. I knew now what words I could use and which ones I couldn't. And so it became more fluid, a better experience for me, less frustrating than it was at the beginning.
Is this computer program you wrote, just out of curiosity, available for anybody who would like to try something like this themselves?
I have when the book came out, I've managed to put up a web page on my website where people can actually use the same rules by typing in a comment box whatever they want. Hopefully, a comment about the book, but actually they can say whatever they want. And so that comment box implements exactly the same rules, and it also gives suggestions for words. When you type the first letter of that word, it will give you a suggestion of available words. And so it's actually a much better tool than the tool that I use for the book, in fact.
Okay, so let's actually talk about the book itself. I wasn't sure what to expect when I first cracked it open, but your book is really quite poetic. It has almost a folkloric or mythic quality to it. Was that intentional?
Well, thank you for saying that. I really appreciate this, because it wasn't intentional. I did not set off thinking, I'm going to write a poetic book about the universe. What I started to do was an experiment. I wanted to see whether this format, this language, which I found quite powerful by and in itself, could be stretched, first of all, to the extent of being able to describe the entire history of the universe. Were there concepts and ideas that I could not explain in any meaningful way using this set of words? That was the driving question and driving curiosity that got me going. But then something interesting happened. This poetic voice, as you put it, actually grew out of the format itself. So the lexicon that I had at my disposal forced me not to use normal words and to launch myself into a more pictorial, metaphorical description of the universe, and hence the kind of mythological character. That's something that actually my readers pointed out to me over and over again, and that's something that I had kind of lost sight of, being completely taken up by the job of writing the book. But finally, when my readers gave me feedback when the book was out there, I was very pleased to hear people saying, well, if sometimes it reads like a folk tale, like a mythological tale about the universe before we had the language to describe things like we do today, or perhaps after a post-apocalyptic future, after we've lost the language to describe those things with their proper nouns, we can come back to them, looking at them with a different, fresher, simpler, childlike perspective, which is what the book attempts to do. But this perspective has been really created by the language itself. It's not something that I set off doing, trying to create and make happen.
It's really interesting to hear you say that, because what struck me as I was reading the book was its similarity to folk tales, to creation myths that you would hear out of our own culture or other cultures around the world. And I hadn't really thought that perhaps that was born out of the choice of words rather than something kind of magical added to it. That was really interesting.
Indeed, and it's interesting to me as well to think about the polarity, about the contrast between the simplicity of the words, or the apparent simplicity of the text, which is only apparent in a sense because there was a lot of sweat and tears and effort going into trying to make it work with those simple words. And so the simplicity of the words, which is on one end, but on the other end, we're trying really to talk about some of the most complicated, complex, and difficult phenomena in modern cosmology, some of the big questions about the universe. What is the dark matter made of? What is dark energy? Where does the universe come from? All of these big philosophical questions, can they be tackled in a meaningful way using simple language and simple words? Well, that's the challenge of the book, and clearly only my readers can tell me whether I succeeded or not in some measure.
And you really don't let the limit of words stop you from diving into some pretty hard stuff in cosmology, in modern physics, which is really quite ambitious given the 1,000 words on the list. Was there anything on your sort of to-do list that didn't make it into the book? Anything you felt you really couldn't tackle with this limit of words?
No, the storyline of the book is very much what I had in mind at the beginning. When I started writing it, the arc of the story came fully formed to my mind simply because it's the distillation, the condensation of hundreds of public lectures I've given over the years. And so I knew what I wanted to tackle. Only when I set off, I didn't know whether I would be able to do so with 1,000 words. And there were some places where it was pretty hard. It was heavy going, and I was at some point despairing that I could find good, apt metaphors I could be happy with that were understandable and pictorial, but equally scientifically accurate to the extent that I could. And so the threshold of quality for me was, can I use this lexicon without compromising on, as much as I can, on the scientific accuracy of what I'm saying? Because to me, that's of course very, very important, and not just to write a tale, but a scientific story that's really accurate as much as possible. And so some parts of it, for example, talking about the very early universe, were very, very hard. How could I talk about what happens in the first fraction of a fraction of a fraction of a second after the Big Bang without using the word Big Bang, without using energy or speed or particle? And so I really had to come up with some new ways of talking about those things. But little by little, this new language, as I was telling before, emerged. And so I started having new terms. So for particles, I could use drops. For supersymmetric particles, I could use mirror drops. And for the Big Bang itself, I could use the Big Flash, and so on and so forth. And so once I started putting together the basic building blocks of my vocabulary, then I had something I could work with. And so the story could be told. But it did feel at times as if I was trying to do something crazy, like, I don't know, crossing the North Pole in flip-flops or something like that, trying to do the most ambitious of things, telling about the story of the entire universe with the simplest of means, which this language put at my disposal.
The areas of cosmology and physics are filled with massive amounts of jargon, and one assumes that jargon is important for people actually working in the field. But based on your experience of this book, how much of that jargon is really necessary for the public to understand?
I think very little, in fact. Yes, jargon is the bread and butter of precise scientific communication between the professionals, and it should be so because we understand it. But the problem is when we, the professional scientists, start talking about our work to the general public, to other stakeholders, to pupils and students, people who do not share our understanding of the jargon, invariably I find that we slip involuntarily into it, even when we don't mean to. And so one of the driving ideas behind the book was, how do we sweep the table clear of jargon? And certainly using 1,000 words does just that, because we take away all the jargon terms and more. And how do we actually start talking about those concepts in a way that anybody can understand? And I found that trying to explain those concepts with these 1,000 words forced me to rethink those very same ideas in a way that I hadn't thought about them before. And so it gave me new eyes, a fresh perspective on my own subject, which I really enjoyed. And so I think jargon is a big problem, and one that we need to solve, also because it seeps into other ways of communication. For example, when I say galaxy or atom or electron, I might assume that you and the public at large might think about those objects in the same way that I do. But I, of course, I'm a trained physicist, and so I have a plethora of ideas associated with those concepts that other people might not have. And so by not using galaxy and using star crowds instead, perhaps we can bring the discussion back on a level where we are all at the same level, and our mental assumptions and mental images that we have as professional scientists do not pollute the conversation, and we can have a much more meaningful dialogue. And that is one of the aims of my book.
In most physics books targeted at a lay audience, there seems to be a sort of tension between the theoretical parts and some of the mathematical concepts. Some books have more of one, while others have more of the other. At what point do we run up against the brick wall of you really need to understand the math when it comes to complex physics ideas? Or do we even run up against that wall?
In communicating with the public, I think the maths are very much in the way, because it is true that at a certain level, and this level is reached very, very early, even at undergraduate physics level, you can't understand those concepts in the way we understand them as professionals without the maths. But then the question that we have to ask ourselves as science communicators is, do we really need or do we really want the public even to understand those concepts to the same level? And is it important? And I think the clear and resounding answer for me is no. It's not important for people to understand general relativity in its minute details and the way we express it in equations, for people to be able and interested in appreciating the beauty of the concepts, of the fundamental ideas behind general relativity. And so I think because the technical language of physics and science is mathematical, the professionals, of course, have to use that language. But because this language is not shared by the vast majority of the population, we shouldn't force people to speak this language before they can approach the beauty, the passion, the fascination of those big questions. And so it is our job, the scientists, to translate those concepts in a way that the people can approach without the maths if they don't have them. And I think that's our challenge. We shouldn't be bogged down in trying to be precise and absolutely scientifically accurate when talking about our concepts with people who are interested in the ideas rather than in the details, the nitty-gritty details of the maths that we use in our everyday work with those ideas.
I've read a number of pop science physics books, and in all of these physics books, they always end up having to pull on your imagination and your ability to kind of picture something in order to explain complex topics or sort of give you a kind of working example. Those sort of just so stories you hear. And what was quite interesting about your book is really asking us to do the same thing, just in a much more simplified way, and really embracing the metaphorical quality of these stories.
That's right. You're very right on this one. And my experiment is just much more radical than all these just so stories that you have described, precisely because I think there is only so much you can say without getting into the nitty-gritty details of the maths, and those we don't need them. And so why don't go all the way and actually use a language that is built, if you like, on purpose, so that the reader's imagination is not only stimulated, it's actually required, it's forced to fill in the gaps that this language leaves in the story, not because the story is patchy, but because the language itself is Spartan, and so it will stimulate you to think about images and come up with your own mental pictures for the concepts that I'm describing. And those mental pictures is all I'm asking of my readers. There is no shortage of great pop science books out there that describe in 300, 400 pages all of the details of the science that it's covered in 96 pages in The Edge of the Sky. But the question is, can we get the general public to be excited enough, enthusiastic enough about this science to go out and read those books or go on the internet and Google concepts that they want to learn more about. And if The Edge of the Sky can achieve that goal of enthusing people, engaging them, and especially people who don't necessarily go to talks about astronomy or don't necessarily buy pop science books about cosmology, if I can reach out to this new cross-section of the public and tell them how exciting, how interesting, how relevant for their picture of the universe this science is, then I'll be very, very happy.
I'm curious, who did you write this book for? Did you have an audience in mind as you were writing?
Not really, precisely because the book is very much an experiment, and I didn't even know when I started that it was going to be a book and that it could be a book because of the reasons that I explained. I just didn't know whether it would work, and at which point I would run out of steam, out of ideas, out of the ability to make it work. And so I didn't set off with a plan and with an audience in mind. Now that the book is finished, of course, I've been thinking very carefully as to what kind of audience would be interesting and interested in reading this book, and what would the book be for them. And I've come to a conclusion that the book really can be read in different ways, and it will speak in different ways to different people. So if you have been exposed to some of the astrophysics and cosmology concepts before, you might whiz through the book and whiz through the metaphors and perhaps chuckle as you recognize this metaphor for that, etc. And might feel good that you can connect the dots in a way that matches your previous knowledge. But my hope is that even if you haven't, and especially if you haven't done this before, reading other pop science books on cosmology, that these new ways of talking about the universe will stimulate you to come up with your own ideas about those distant concepts. And hopefully students and young adults and even children will be able to read it and enjoy it. I've had comments from readers saying that they've been reading it to their 5-year-old children, and they've loved it, and they've come up with lots and lots of questions about the universe, which is exactly what I want to achieve. So if any of this can come to pass, then the audience of my book will have found a way of actually getting in touch with those concepts. And so I like to think of The Edge of the Sky as a book for children of all ages.
Student people are different from other people. They spend their entire life asking questions, and as soon as they have found out the answers, they start all over again with new, harder questions. They love questions, and they never run out of them. The best questions for student people are the ones that begin with why. These questions are also the hardest. This is Science for the People, and I'm Rochelle Saunders. I'm here with astrophysicist and author Roberto Trotta talking about his new book, which we just heard an excerpt from, titled The Edge of the Sky, All You Need to Know About the All There Is, and how to explain complex cosmology without complex words. As you were writing the book, did you get any feedback from readers, sort of test readers, I guess would be a good term, who maybe weren't as familiar with the topics as you were?
No, almost none. Not until the very first draft was ready, precisely because I didn't want to... First of all, I wasn't sure that the book was going anywhere, so I wasn't comfortable in sharing my little experiment with anybody else until I felt that it had something of some value. But then... when I was almost through with the first draft, I showed it to a few friends and to my wife, who is not an astrophysicist, and their feedback was really, really interesting and really, really useful to me, because I could then see what kind of metaphors didn't work, what kind of pictures were too complicated or were too involved, and through many, many revisions, I finally polished the text to a level I was happy with, and my test readers were also happy with. But it wasn't a structured process. It was more, okay, I'll set off with this experiment, I'll see what I can get, and once I'm fairly happy with it, let's see what other people think, whether there's any value to it than the value that it had for myself, because I wrote it. And so it wasn't a systematic process at all.
So for someone who has chosen to enter the world of physics through The Edge of the Sky and is inspired to learn more, or who has some questions, where do they go next?
Well, there's a large number of great books out there about the fundamental nature of reality, and they're written in beautiful prose, very clear language. And so out of the top of my head, I can think of the books by Brian Greene or Sean Carroll or John Barrow, and any of those three authors and many more have written very lucidly and from a scientist's perspective about those deep questions about the universe. And so I definitely recommend any of those authors and their books to deepen from a different perspective and a different point of view the kind of ideas that I've sketched in The Edge of the Sky.
Roberto, thank you so much for being here. I loved your book. I thought it was beautiful, and I hope it will be appearing in many Christmas stockings.
Thank you very much, Rochelle. It's been a real pleasure.
If you want to learn more about Roberto Trotta, his work, or his new book, The Edge of the Sky, All You Need to Know About the All There Is, you can start at his website, robertotrotta.com, a link that you'll find on our website at scienceforthepeople.ca. Speaking of our website, if you haven't stopped by in a little while, you may have missed our store, where those of you wanting to show your enthusiasm for Science for the People can find a few select items we hope you'll enjoy. Those of you we've met will know that our team takes its coffee intake very seriously. So we've created an official Science for the People coffee mug, available in both an 11-ounce size for modest caffeine drinkers and a 15-ounce size for those who need a little more to get going in the morning. We've also added a range of shirts and hoodies in men's and women's styles for those who'd like to wear the Science for the People colors and spread the word. To check out our official Science for the People branded store, visit our store website at scienceforthepeople.ca/store. And if you do, we'd love to hear your feedback. What official Science for the People items do you love? What other items would you like to see made available? We always love to hear from you. You can email us anytime at feedback@scienceforthepeople.ca. Send us your thoughts on the most recent show or pass along your ideas for new shows. You can also leave your thoughts in the comments on individual episodes on our website, send us a message or comment on our Facebook page, or tweet at Sci for the People anytime. You can also find us on iTunes, where you can access all of our previous episodes and subscribe to have new episodes delivered right to your computer, phone, or tablet as soon as they're available. And if you enjoy our show, please do consider leaving a review on iTunes and sharing the love. As always, thanks for listening, and we'll see you next week on Science for the People.
Science for the People is recorded in Edmonton, Alberta. The show is produced by Rochelle Saunders. Ryan Bromsgrove is our promotions manager. Our social media manager is Chelsea Butler. K.O. Myers updates our website. Helen Quivalon is our publishing liaison. Ed Haynes is our guest coordinator. We get research help from Josh Witten. The show is edited by K.O. Myers and Ryan Bromsgrove. Our theme song was written and recorded by Fractal Pattern, and its title is Binary Consequence. The show is hosted by Rochelle Saunders, Marie Claire Shanahan, and me, Desiree Schell.